In the design of any building, one of the most important steps is to test whether the structure is sufficient. A structure has to resist loads, such as its own weight, the weight of snow on the roof, or the force of wind. For unusual structures, like a grid shell, there are no rules of thumb, and getting an accurate prediction of how a structure will behave is difficult. Luckily, my mentor, Professor Mohammed Balhassani, is a structural engineer and teaches the structures courses at the Spitzer School of Architecture, which I attend. Since doing structural calculations on a structure with as many parts as our grid shell would probably take a whole semester, it was clear that we would have to choose an appropriate software. At first, we considered using SAP 2000, an older software that my professor had more experience with. However, a newer software, Caramba, works as a Grasshopper plugin and would allow us to update the analysis in real time as we adjusted the design. Caramba is a finite element software, which means it analyzes the force on small parts of a complex structure to create an overall structural analysis. To verify that I was getting correct results in Caramba, I tested the same structure in both softwares, and luckily the outcomes were nearly identical. So, to set up for a structural analysis in Caramba, I had to define several conditions. First, I defined the supports. This is where the structure connects to the foundation. As well as the location of the supports, I had to define whether the connection can move or rotate. In this case, we chose a fixed moment support. The next thing to define is the material and cross-sections of the members. The software uses this to calculate how much load each member can take. For my design, I am using 3/4 inch by 1.5 inch oak members. Next, the lines of the grid are converted into beams with the material and section properties. As well as the beams, I defined a shell element for each of the grid shell cells because the stiff cladding actually acts like bracing. It took me a while to figure out this was necessary, but it vastly improved the performance of the structure. The next step is assigning the loads. A combination of the loads is assigned with specific magnitudes at specific points. The loads are also multiplied by a safety factor. In this case, I assigned 1.2 times the weight of the structure, as well as 50 pounds per square foot on the outside surface. I also assigned a load of 150 pounds applied to individual joints one at a time to represent someone climbing on the structure during construction. Once the beams, the supports, and loads were assigned, I assembled them into a model for analysis. And the good news was that my structure was more than sufficient, especially after adding the cladding as bracing. We considered increasing the spacing between the laths in the grid to make it more efficient, but found that the resulting form was less desirable. After analyzing the model, Caramba can display the results in a variety of useful ways. Displacement shows how far each part of the structure is moved when applying the loads. In this case, the displacement is negligible, with a maximum only about 1/32 of an inch. This is partly because the structure is close to a funicular form, and a funicular form is structurally the most efficient form. Another way to view the structure is by its utilization. This shows how much force each of the members is taking compared to what it could take. For example, if the utilization was 100%, that member would break. Almost all of the structure was under 12% utilization, and that's easily good enough. As you can see, only small parts of the structure are in tension, which is the blue parts, which means it is quite efficient. You might wonder, if this type of structure is so efficient and simple, why is it used so rarely in architecture? A big part of the reason is that it's hard to predict how a structure with hundreds of differently oriented parts will behave in real conditions. Luckily, I had some first-rate software and an expert in unusual structures, that's my professor, to help me out.